In this video, we're going to look at chemical kinetics. When we think of the word kinetics, we usually associate it with movement. So chemical kinetics is simply the study of how quickly or the rate of a chemical reaction. So if we look at the example of sulfur reacting with oxygen to form SO2, the reaction rate is going to be the amount of SO2 formed over a change in time. Now, this is if we are looking at the reaction with respect to the products. We can also look at the reaction with respect to the reactants. So we can also say that this is going to be equal to the amount of sulfur used over the change in time. And that is if we look at it with respect to sulfur, but we can also look at it with respect to oxygen. So the amount of oxygen used over a change in time. So these are different ways that we can look at a reaction rate. There are a number of things that will affect the reaction rate, and one of those is the idea of collision theory. So, in order for a reaction to happen, there's a lot of things that need to take place. So, the molecules of the reactants must collide. They must collide in order for a reaction to take place. And not only must they collide, they also need to have enough energy. So reactions are going to start out fast and then they're going to tend to slow down due to decreasing the frequency of collisions between reactants. But before they can even collide, or before we can even have a reaction, they have to collide. And it has to collide with enough energy. And finally, the colliding particles must be properly oriented in order for a reaction to take place. So if we look at this diagram right here, in A, we have the improper orientation, incorrect orientation to make a product. In B, we don't have enough energy, so the reaction is not going to go. In C, we have enough energy, the molecules collide, and they have the proper orientation to make the desired products. The accumulated degree hours, whoopsies, or we just simply refer to this as ADH, is very important with kinetics. And this is where we look at insects, and it looks at the number of hours an insect spends developing and multiplies by the temperature of each hour. And this is very important in forensic chemistry, where a lot of decaying organic matter can start having bugs grow in them, insects grow in them. And so if we take the hours that insect is developing and multiply it by the temperature at each hour, then we can get the ADH. So if we have 8 hours that have gone by for the insect's maturity, and the temperature is 25 degrees Celsius, we can take 8 times 25, and that's going to give us an ADH of 200. It's going to be 200 ADH. If we have that exact same insect, but instead of 25 degrees Celsius, we're looking at 20 degrees Celsius, we can figure out how long it will take. We know that the ADH is 200, and I know that the temperature times the hours is going to equal to 200. So I can simply take my 200 and divide it by 20. So it will take 10 hours. Biochemical growth reactions are faster at higher temperatures. So the higher the temperature is, the faster the reaction is going to take place. And we can see that because at 25 degrees Celsius, it takes 8 hours to get the 200 ADH. If we lower that by 5 degrees, now we add 2 hours to get the same ADH. Generally, an increase in temperature of 10 degrees will double the rate of the reaction. So we can use temperature to speed up a reaction, but we can also use what is called a catalyst. Now, chemiluminescence, chemiluminescence is a chemical reaction. And what happens, it's really fun to see, is we get this emission of light through this chemical reaction. And remember, emission is just a fancy word for gives off. So you see light as a result of this chemical reaction. A catalyst is something that is going to increase the rate of the reaction. Blood, it contains iron, and the iron can be a catalyst in the reaction of luminol and hydrogen peroxide. When luminol reacts with hydrogen peroxide, we get chemiluminescence. We get this emission of light through the chemical reaction of luminol and hydrogen peroxide. So you can use luminol and hydrogen peroxide to detect the presence of iron. And you can see if something will start glowing. Let's talk about how a catalyst works. So the activation energy is the minimum amount of energy required for a chemical reaction to take place. So if you don't meet that activation energy, then your reaction is not going to happen. In order for a catalyst to work, it works by lowering the activation energy. In this diagram, we have an uncatalyzed reaction and we have a catalyzed reaction. So here are the energy of my reactants. In order for my reaction to take place, I have to get all the way up here to this energy, and then I will proceed towards my products. So the difference between the energy of my reactants and the energy of the highest peak is my activation energy. If we look at the same diagram with a catalyzed reaction, notice that the activation energy is much smaller. So it provides a different pathway for the reaction to take place. And in doing so, it's going to make the reaction faster. If I don't have to reach as high of an energy in order for my reaction to take place, then it's not going to take as long. Now we have two types of catalysts that we're going to talk about in this class. We have a homogeneous catalyst, and a homogeneous catalyst is going to be in the same physical state as the reactants. And so it's going to have the same state for the reactants and the catalyst. A heterogeneous catalyst, out. So a heterogeneous is going to be a catalyst that is not going to be in the same physical state as the reactants. And generally, it's going to be a solid substance, and it's going to provide a platform or a surface for the reactants to adhere when they go through the reaction. So it gives them kind of a platform for the reaction.